The broadcast is now starting. All attendees are in listen-only mode.
Welcome to the webinar, An Introduction to Multivariate Analysis with the Unscrambler X. My name is Tracy Solfrank. I'm a Senior Account Manager for Camo. While waiting for other people to log into the webinar, let me take just a few minutes and tell you a little bit about Camo. With over 25 years of experience in developing multivariate analysis software and solutions, Camo is viewed as an established and trusted market leader. Creating significant value for our customers is at the center of what we do. In fact, we've saved companies millions of dollars through improved process control and have assisted other clients develop best-selling products. Overall, whatever your data, we can help your company save money, increase revenue, and turn your data into a competitive advantage through better analytics. Over the years, the Unscrambler has been used in essentially all market areas and verticals, from chemical, food and beverage, agriculture, energy, and pharma. And the Unscrambler can be used in various functions across an organization, from R&D to product development, Q&A, QC, and process analytical technology, just to name a few. We were founded in 1984 by a group of scientists in Norway who developed software for a handful of clients in the food and beverage, and the oil and gas, and the pharma sectors. Camo was founded in 1984, and over the years we have built a reputation among some of the largest and best companies in the around the globe. Today, we have over 25,000 end users of our software around the world. In fact, the Unscrambler is even used by NASA on Mars on the rover Curiosity for the classification of rock samples. Over the years, Camo has grown into a global organization with our corporate office located in the Oslo, Norway. We have additional operation and support offices in Woodbridge, New Jersey, to service the North American market, and additional support offices in Tokyo, Japan, Sydney, Australia, and Bangalore, India. This overall gives Camo genuine global reach and the ability to service our clients wherever they are. Many of the world's largest companies are Camo's clients, and as you can see, these are recognized industry leaders. Our product portfolio includes our flagship product, the Unscrambler X, for multivariate analysis and design of experiments. The Unscrambler is suitable for a wide range of data analysis tasks, such as exploratory, regression, classification, and prediction. We also have complementary software which allows the use of our Unscrambler models to be deployed in real-time analysis in a production environment through our analytical engines, which can be embedded into third-party software, and then Process Pulse, which is a standalone piece of software for real-time analysis. In addition, Camo has a full range of professional services, including consultancy to assist in model building, and we also offer training in multivariate analysis, as well as a complete range of IT solutions and customization. Today we have presenting Camo's chief scientist. Her name is Dr. Catherine McCabe. She holds a PhD in polymer science and is an expert in spectroscopy and chemometrics, and has a wealth of knowledge in multivariate analysis. And with that, I'll turn it over to Dr. McCabe.
Thank you, and welcome to today's webinar, where I'll be talking about multivariate analysis and showing you an example of using this within the Unscrambler X software. So what is multivariate data analysis? It is a combination of techniques that allow us to model patterns and relationships in our data between many variables and simultaneously, so that we can, from this, extract the information from the data that we've collected. There are many multivariate tools that serve different purposes. It starts with the design of experiments, which allows one to do systematic experimentation to gain maximum insight from the minimum experimental effort to understand the effect of given inputs to measured responses. We also have exploratory data analysis, which includes the tools of principal component analysis, which I'll demonstrate today, as well as cluster analysis and multivariate curve resolution. These tools help us to see important groupings in our data and the overall patterns in the relationships of our variables to our samples, and can be used to help us define classes or species of materials. For classification and discrimination, wherein we're interested in identifying new species based on given and well-defined modeled groups, we can use principal component analysis classification, PCA classification, through SIMCA, soft independent modeling by class analogy, or some advanced classification tools such as support vector machines or linear discriminant analysis. Oftentimes our objectives are to be able to predict quantitatively a new value from samples after having built a model from different variables that have been measured over calibration samples. For this we use regression modeling, most commonly partial least square regression, PLS. We also have the ability to use principal component regression, multiple linear regression, or support vector machine regression. Exploratory data analysis or data mining really helps us to see the hidden structures in our data in complex data sets. In this depiction here, I'm showing a three-dimensional PCA scores plot, which is showing us that we have the similar trajectory over three or more different batches of data that have been collected. This approach can be used quite well to help us visualize patterns in our data and to see whether or not we have similarity and differences between samples, batches, or whatever our data may comprise of. We can also do classification, which is this classification or separation of groups of objects based on the similarity of them from the measurements that we've made. The purpose is so that we can classify a new sample into the correct category. So in this PCA scores plot, I actually have different groups, classes of materials that have been measured, and from this we can build up classification models so that a new sample could be identified as being in one of these classes or indeed not being any of the modeled classes. Regression analysis allows us to develop quantitative models from existing data to predict a response. So we can describe the relationship between measured X variables and a response variable Y so that we can get a model. The predicted versus reference plot shown here shows a good linear relationship between these samples for which we're measuring the octane value in gasoline from spectroscopic measurements, so that when we have a new measurement, we can then apply the model to predict the value of gasoline. And this is used quite commonly in the petroleum blending and refining processes. We use multivariate analysis across many applications to generate simple models of complex systems. So it's used for design of experiment in terms of formulation and product and process development. We can use it for optimization, for process improvement and capability studies. We can use it for monitoring of processes as well as for analysis and exploration of our data, for quantitative calibration based on any number of types of data, and for process control where we can do model predictive control and predictive analytics. Multivariate data can be of many different types, and here I'm showing just a few examples, including some instrumental data, process data, sensory data, and indeed product data, such as information about products, properties, their price, consumer preferences to those, and the demographics of consumers. One of the important things about multivariate analysis is to follow a logical flow in doing the work, beginning from defining analysis objectives, then to collecting the data, checking the data for its validity, making models, which is an iterative process, checking the model to validate that model so that we can apply it on new samples to get the results. So we use the various tools as we go through our workflow, starting with design of experiments through to prediction and real-time analysis to get our results, where we do our calibration and cross-validation using tools such as PLS and PCR. So in the introduction to the Unscrambler, I'd like to begin talking about data collection, import, inspection, and preparation for analysis. It's important when we're doing our analysis that we have data that are representative of what we're interested in measuring. Samples need to be representative with respect to the properties that we're looking to measure, the different sources of variability that we may expect to have in our population, so the different levels or concentrations of things we may have, samples from different sources, and so forth. It's difficult to put a strict rule on how many samples are enough. Indeed, we need to have the sufficient number of samples to properly describe the population that we're looking to model. And if we'd like to have a general model, one that covers an entire population, then we want to be sure that we include within that samples that are at the extremes, far away from the center of the population. Whereas for a robust model covering more of the typical samples, we may do some sampling where we're taking samples just from what is perhaps closer to the normal operating range of what we're interested in measuring. Regardless of our objectives, it's important that we properly select data and collect samples to collect those data, because the important thing is garbage in gives garbage out. No software program should find information where none exists. When we have our data, we then want to import it into the Unscrambler, and here you see that using the file import data, one has many different data types that can be directly imported into the Unscrambler, including many proprietary instrument formats. One can connect through a database. One can also use OPC queries from a plugin with that, or with plugins for My Instrument drivers as well. When we've imported our data, we need to organize it into rows and column sets so that we define which data are being used for which part of the analysis. This shows the define range dialog within the Unscrambler, where you see that one can define row ranges, which are groups of samples, and column ranges, which are the definition of the different variables that are organized into the different columns of our data. We can also use special intervals so that if we have category variables in our data, we can define row sets based on those entries, or indeed choose samples randomly based on all the samples that are in the data set that we are using. Another important step is to visually inspect our data, and there are many different plots that are available to help us to really visualize and look for patterns in our data. It's important to start by looking at our data to see if indeed we have any anomalies, to see if there are any trends or patterns in our data. And indeed, line plots of instrumental data can be very beneficial, as can multiple scatter plots, to see if we have any relationships between any of the variables to each other. We can also, during the visual inspection of our data, see if we have any outlying data or perhaps some mistakes that we'd want to correct before moving forward in our analysis. Another great tool for helping us explore our data are to do descriptive statistics, which are accessed under the Tasks Analyze menu as the first analysis available. And in descriptive statistics, we compute the quantiles, which gives us the box and whisker plot, which shows us the minimum, mean, and max value for each variable, as well as the 50 percentile, from 25 to 75 percentile of our data. So from this we can get a feel for the variability of our data as well as the different scales of values within our data sets. A useful tool within the Unscrambler is the ability to define variables as category variables. As if we use category variables, we can use this in sample grouping so that we can color code our graphics, which can help us then to visualize and communicate the results. Here I'm showing an example where I have data which are related to different pharmaceutical excipients, actually spectral data, wherein because I have a column of category variables, I'm able to color code my line plot of those data based on the different categories, as well as my PCA score plot. So I can distinctly see not only that I have groups, but what those groups are related to and that they are unique for the different categories that I've defined. So now I'd like to show you some examples of importing, inspecting, and organizing data. So I'll turn to the Unscrambler, wherein this is the user interface for the Unscrambler X. And we import data by going to the File, Import Data menu. And indeed, we can import data from Excel. And here I'll import some process data from Excel. And you see that we can handle the latest Excel version as well. And you get a preview of that data. So I can see that I have here 40 rows and 10 columns. And I can import all or some of that data. Here I'll import all of those data. And they are now added as a data matrix into my project navigator. I can import data from proprietary instrument format. So I'll import here some spectral data that we'll use in our analysis, where here I'm importing some spectra which are all in a folder here where I can select all the matching data here, and I can get a preview of those data. So I'm selecting 29 samples here to import. So I can also define to include the file name for my sample name. And now I've imported my data, which happen to be, in this case, some near-infrared spectra of ethanol water mixtures. For this data, what I'd like to do is develop a quantitative calibration. So I need to then also import my reference values for what the concentrations are for these samples. And I do that by going File, Import Data, Excel, and here I have in an Excel spreadsheet my reference values for what the concentration of ethanol is for all these 29 samples. I'll import those data. It's a separate matrix now, but I would actually like to copy this matrix and insert it here with my other data. Insert copied cells. Name that my ethanol, as that will be my response in developing a quantitative calibration. So I'd like to do some defining of my data. I right-click here to create this as a column range, and this will be my ethanol. And I'd like to actually define my other columns, and I'll do that by going to the Define Range dialog. All the other columns from column number 2 and holding the Shift key and highlighting over to column 2128, these are my near IR spectra. So I give that column set a name, create that, and I'd also like to divide this sample set of 29 samples into 15 samples as a calibration set. So the first 15 rows here I highlight and create this row set as my training set, and I create that. And I'd like to use my remaining rows as my test set. So I can use my invert selection button to choose those, and it's now highlighted the remaining rows in my set, and I'll call that my test set. So I've created here 2 row ranges and 2 column ranges I now have. I could create many more for that. So I now have in my project navigator, under my data matrix, I have 2 subsets, a row set, 2 row sets, and 2 column sets of the data. Another good exploration tool for our data is indeed to do some descriptive statistics. So here I come to my other data matrix here where I have some different variables that were measured in a processing scenario. So I'll go to Tasks, Analyze, Descriptive Statistics, and I will look at now the descriptive statistics, the quantiles, and the mean and standard deviation across all the different variables that I've measured. And here you see these are actually the individual box plots for every one of these variables, and you see that they're actually quite small and there's little variability in this particular data set. So that is a little bit about how we can import data, organize the data using our define range, as well as some plotting functions. But now I'd like to talk a little bit about the principal component analysis, which is one of the key exploratory data analysis tools in multivariate analysis. PCA is a means to extract information and remove noise from our data by computing the principal components, the latent variables which explain the structured variance in our data. So by computing the principal components, we reduce the dimensionality of our data from its original dimensionality to that which is carrying the structure of our data in terms of the principal components. It is a superior tool for exploratory data analysis and can form the basis for classification and identification. From it, we can also achieve variable reduction, use it for process monitoring, and get a visual analysis of variance. So what we're doing when we're doing principal component analysis is we're taking a matrix of data, X, which is comprised of many samples and variables, and developing a PCA model which is comprised of the different principal components which are carried the structured variance in our data, and bundling the remaining part of our data into error terms, which are actually the noise, the unstructured variance in the data. When we run a PCA analysis, one of the key outputs that we get is a score plot. A score plot is a two-dimensional, typically, plot of the projection of our original objects into the new coordinate systems of principal components. PC1 and PC2 are our axes, so our samples are projected into this new coordinate system. And from this we get a map of our samples, and samples that lie close to each other in a score plot are samples that are similar. They have similar variables and measurements. Samples that are far apart are dissimilar. So from a PCA score plot, we can get a picture of the spread of our data, and indeed if we have any groupings or indeed outlying samples, because samples that are very different from most of the samples will be very far away in the score plot. Here I have a three-dimensional score plot showing mass spec data that was collected on different serum samples for subjects who have ovarian cancers and those who are control samples. And we see that in this PCA scores plot, which I've color-coded based on the different categories, that we can, from this data, get a very good separation and groupings of these different types of samples. And we could move forward with analysis to use this as a means of classification of these types of samples. So the score, which is what I've been showing, is actually the distance from the mean of all the samples along a principal component. So it is actually the position within this new coordinate system for each sample. We also compute, when we do principal component analysis, the loadings. The loadings are the direction of the line that is describing this principal component, and it's telling us the relative contribution of our original variables, x1, x2, x3, to our principal components. So it actually is telling us the relative importance of our original variables in explaining the structured variance in our data. I'd like to now show a demonstration of doing a PCA analysis, and for this example I'll use some data on raspberry jam. In this data we have 12 samples that span jam quality, and we have 18 different variables that have been measured. 12 of these are sensory variables that are scored by panelists, and we provide the average values for the different panelists for all of the 12 sensory variables that I have shown here. We also have 6 instrumental measurements that include the color, absorbency, solids, and acidity of the raspberries that were made into the jam. So we also within this have samples that are from 4 different locations, cultivars, and that span 3 different harvest times. So we want to have an understanding of the relation of these samples to each other and the samples to their properties. So turning to the Unscrambler, I have here my data for my jam, where the data is comprised of 12 samples, and within my data set I have the first column of harvest time, which is a category variable telling when these samples were harvested, a category variable of the cultivar, and then I have the rest of my columns of different variables that are my sensory variables. I actually have in here a preference value, consumer preference for the products, as well as instrumental measurements that were made on these samples. So I'd like to get a picture of these data, and I'll do this by doing a principal component analysis, which I do by going under Tasks, Analyze, Principal Component Analysis, and I need to choose my data matrix and the rows and columns I'd like to use. For my rows, I'd like to use my training samples, and for my columns, my variables, I'd like to use these 18 instrumental and sensory variables together. By default, the software is looking to compute a maximum of 7 principal components, and it mean centers our data by default as well. In this case, our measurements are in very different units of measurement, so I'd like to weight my data. I do this by going to my Weights tab, selecting all my variables, and applying my weighting of center and standardizing my data. So I click Update to apply my weights, and then it's important from these model-driven or data-driven models that we always validate. So we go to the Validation tab, choose Setup, and for this small data set, we'll use a full Leave One Out cross-validation. Clicking OK, my PCA overview is now displayed for me, where my scores plot here shows a map of my samples, and this is showing blue and red for calibration and cross-validation results. I did a full cross-validation, so every sample participated in the model and in the cross-validation. I toggle that off so that I can look at my scores plot and color code this based on the category variables. I do this by right-clicking, choosing Sample Grouping, and I'd like to choose my column of harvest time. I create row sets based on the entries there, so I have row sets now for the harvest time H1, 2, and 3, and I can apply this to my graph, so I color code my graph, and from this then I can see that there is, within this data of 12 samples, first of all, my first principal component explains 43% of the variance in the data, but indeed I can see that most of the samples on the left are those that were harvested early. Then we go to the harvest time 2 and to harvest time 3. So there is a structure to my data, these samples, based on the harvest time. Now what are these patterns related to? Well, there we go to our loadings plot, which is a map of our variables. And here we see that on this PC1 axis, 43% of the variance, we have a strong negative contribution of the variables here, which are thickness, and I can zoom this in so we can see that the other variables are the colors LAB from the APHA color. And these variables are very close to each other, meaning that they're correlated to each other. Now on the opposite side of this PC1 axis, we have absorbance, redness, and color. So the PC1, 43% of the variance, is dominated by the variables that are along the PC1 axis here. And we have these variables correlated to each other and anti-correlated to these. The PC2 axis, explaining 27% of the variance of our data, is dominated by raspberry smell and flavor and off flavor. So from this data set, we then can project where new samples would lie based on these properties, but we also have a sense of which properties are related to which samples. So these samples here, harvested late, have higher values of the properties of the absorbance, redness, and color, whereas these early harvest ones produce a thicker jam and their color values are lower for these. So in this PCA analysis, we saw in our scores plot that we have some groupings based on the harvest time for these 12 samples. We see from the loadings plot that these variables here are related to each other and anti-correlated then to the absorbance, redness, and color. And these are the dominant variables in explaining 43% of the variance, whereas PC2 is descriptive of flavor, and we have off flavor anti-correlated then with raspberry smell and raspberry flavor. We can bring this data together into a single plot in the biplot, wherein now our samples are in blue, our variables in red. And here then we can relate the relative positions of samples to variables such that we can state indeed that these samples have highest values of the redness and color. These that are close to these properties, variables, have more juiciness and shininess as well as sourness. And these have the greater thickness. Now I'd like to talk about partial least square regression, PLS. What is regression modeling? But actually, it's a mean by which we develop a model so that if we don't have a direct means of measuring something, we can do that from a model. But in order to do this, we need first to develop that model. So imagine if we wanted to measure the weight of samples but didn't have a balance. One relationship that exists in nature is that the displacement of a spring is related to the weight of the samples on that. So we could relate this measurement using calibration standards to measure how much that spring displaces with known weights, and then develop a regression model, where here we're looking at a single response versus a single variable, where we're relating the length of the spring displacement to the weight that we've applied. But we then have an equation which we can apply to a new sample to get a prediction for what the weight is for our unknown sample. What we're looking to do is expand this to the multivariate case. And there are numerous regression methods. The simplest extension of the univariate case that I showed with the spring displacement is multiple linear regression, wherein we can relate a single response, such as the weight, but to numerous input variables. When we have many variables, though, we'd like to actually relate those many variables to our response y, and we can do this using principal component regression, which first decomposes our x data in terms of a PCA and then the regression of the PCA scores versus our y response. Or we can use a partial least square regression, which models both x and y simultaneously. So when we do a PLS regression, we're looking to find the interrelationship that best describes the variance in x that describes the variance in y. So with PLS, we're aiming to maximize the covariance between our x and y. And this is what differentiates it from PCR, but it also is what allows us then to have fully interpretable models, because we have with this the scores and loadings relating our samples and our variables directly back to those data and how they were measured. I'd like to demonstrate doing a regression analysis in the Unscrambler, and here I'd like to show this for the near IR spectra of ethanol and water, which I showed you how to import. So what I have are data of near-infrared spectra with varying concentrations of ethanol from 15 to 85 weight %, and these samples were prepared gravimetrically. What we'd like to do is show the proof of concept of making this measurement to enable development of online monitoring methods. And here I've highlighted actually the near-infrared spectra, showing that we have regions of the spectra that are related to the chemical makeup of our ethanol water mixtures. So if I come back to the Unscrambler now, I'll again come to the project that I was just working in, where I've actually also have within this project the near IR spectra of the ethanol water mixtures, wherein the data are organized such that I have the row set of my test set of 14 samples and a training set of 15 samples. I have a column set of the ethanol concentration here, and I can make a histogram plot of this, so I can see that indeed I have quite an even distribution of the ethanol concentration across the samples, as is required in order to do a calibration model. Within this data, I have the spectra that, oops, I'm sorry, I hit the wrong button, the spectra that span the entire range from over 2,000 variables. So in order to develop this calibration model, actually, I have created a new variable set, a subset of these, which is focusing on this part of my data alone, because I want to remove this instrumental phenomena here and want to focus on this region. So here I have a column set that I've created called Analysis Region, which I can right-click and plot this, and we see the spectra that we'd like to relate to our concentration of ethanol. And we see that we have very systematic changes in the data here. In order to run a PLS regression, I come to Tasks, Analyze, and here I choose my partial least square regression. You see that I have the ability to choose MLR, PCR, PLS, indeed LPLS and SVM. Here we're focusing on using the PLS regression, where it brings up my PLS dialog, where my first point is to make my model inputs, where I need to define my predictors, my X data. And in this project I have numerous data matrices. I need to make sure that I choose my correct data matrix, in this case my near IR spectra. The rows, or the samples I'd like to use for my analysis. Here I want to use my 15 training samples. The columns, I'd like to focus just on these analysis region of 941 variables here. And for the response, those responses are also in the same matrix, so I choose that matrix again. And of course, I need to have the same number of responses as I have predictors. So for my rows, I again choose my training set. And here my response is my column set of ethanol. Again, the software default is to compute 7 principal components, and though we have 941 variables here, our data are highly correlated, and one reason for using our PLS is so that we can use the information over those 941 variables, but use the partial least squares, the PLS factors that are explaining the structured variance in that data. So with this type of data, where it's all measured in the same way, we do not apply weights, so we won't apply the weights, but we always validate our models, and we do a cross-validation, going to the Validation tab, cross-validation, Setup, and again, with such a small group, I'll do a full cross-validation. We do have the option to use random, custom, or even systematic cross-validation, which one should use if you have copies or duplicates in your data. You should use systematic cross-validation. So coming back to my Model Inputs tab, we see we have a summary here of my settings, and clicking OK, my PLS then runs, and I'm asked if I'd like to view my plots for my model. Clicking yes, it brings up my PLS overview graph of 4 graphs, and it's also added a node into my project navigator named PLS. And if I want to get the details of what this model are, I can look in this small box here in the lower left corner, which has a summary of all the settings that were used to develop this PLS model. But now we'd like to look at our model overview. And in the PLS regression overview, we have a scores plot, as we do for our PCA, a map of our samples, again with calibration in blue and cross-validation in red. I can toggle that off. And we see that we have a systematic change of our samples across this. I can see if indeed this is related to my ethanol concentration, as I expect it is, for that is what we're modeling. And we can see in our predicted versus reference that we have a very good linear fit for our model. But I can add sample grouping to my score plot by right-clicking, choosing sample grouping, and now I can choose my column set now of ethanol, and now I can create row sets based on the value in my ethanol, which is a numeric value. It's not a category variable, but I can have it set up, create groups of equal width across the range of this value, and I'm choosing 3 groups, basically relating to low, medium, and high concentrations. And it now has 3 ranges, and I can color code now my scores plot with this information. And I see that indeed, as I go from left to right in my scores plot, I'm going from my low range concentration of ethanol to my high range. And indeed, here we see that one PLS factor, we have 100% of the variance in X that explains 99% of the variance in Y. A very good correspondence of these spectral data to the ethanol concentration that we're looking to model. Indeed, the regression coefficient shown in the upper right quadrant is a graphical representation of what our model equation is. And from this, we can see that there are some variables that have a very small contribution to our model, but yet we have some variables that are very important to this model. And we can see that this regression coefficients do indeed resemble what our data themselves look like. So we can see that, so we can with assurance see that we are indeed modeling directly the relationship between the spectra and the ethanol concentration. Our explained variance curve, also shown with calibration and cross-validation. I can add a legend to this plot by clicking the legends icon. So here my blue is my calibration and red cross-validation. And this is indeed the explained variance as we add successive factors to our model. And for this data set, indeed with a single factor, we're explaining the full variance of our data. And indeed the software is recommending that it is a single PLS factor model. Our regression coefficients are shown for a single factor model. Our predicted versus reference for a single factor model. And here we see our model statistics, where we see that our root mean square error of calibration is 1.8, and that for cross-validation about 2.4. So this is, in summary, how we develop a calibration model. So we did the PLS regression, and from the beta coefficients can see which variables contribute in modeling this system and relate that back to our raw data. But one of the important things about modeling is that we then want to do predictions from our models. And prediction is actually straightforward once a model is built. What we want to do is predict unknown samples. And for this, all of the model parameters are defined in the model, including if we had applied transformations to the data. And what we want to do is apply the same number of components, in the case of our ethanol data, a single component, PLS factor, to new data, and the data need to be of the same dimension, and it should be of similar samples. Now, when we do prediction, outlier detection remains essential. We need to ensure that the samples that we are predicting on are similar to those we've used in our modeling stage. In the Unscrambler, we use deviation and outlier tools as a measure of similarity of predicted samples to those in our calibration set. So we can do prediction within the Unscrambler itself, which I will illustrate to you, or indeed in some of the products that Tracy mentioned. We can do real-time prediction using the Unscrambler Process Pulse, a standalone real-time analysis software, or in third-party software that has our engines embedded in it. But let me show you doing a prediction within the Unscrambler for our test set. So you may recall that we had some test data within our data set. In order to do a prediction, we go Tasks, Predict, and I choose Regression. And I'd like to choose the model. So I have my model, PLS ethanol. It is a single component model. And I'd like to do a full prediction, including looking for inliers and outliers. And I'd like to apply that model to the data that are my test set. So I need to have my data be in the same dimension as my model itself, so 941 variables. If I chose another set of variables, it would not be able to proceed, so I choose my correct set of variables. And because I'd like to compare that with what my laboratory values are to give me a standard error of prediction, I also include my Y reference value by choosing again my test samples and my ethanol value. Clicking OK, I then get my prediction results, where in the Unscrambler, by default, our view is predicted with deviation, where a small deviation, given by the blue box here, indicates that our samples are similar to the samples on which we've developed our model. So we have in our table our predicted value, this deviation value, which is a measure of the residual and leverage of this sample to our calibration set, and indeed the reference value, which I gave it from the data set. We also would like to see the statistics on this model, so we can look at prediction, predicted versus reference, where here we have then our standard error of prediction, 1.1, quite in line with what our root mean square error of calibration and cross-validation are for these data. As I mentioned, outlier detection is also important on prediction, and here in our predicted with deviation plot, we do get predicted values for every sample, and no sample has a very large deviation, though for these lower concentrations the deviation is larger than for these. Another very good outlier tool is to look at the Hotelling t-squared, or indeed the inlier plot, which we can access by going to Plot, Inlier Hotelling t-squared, and we can choose the biplot of these together, where I now have the limit lines for the inlier, which is a nearest neighbor outlier, or the Hotelling t-squared, and these limit lines are computed from the model itself. So here we can see that safely all of the 14 samples in our test set fall within the range for this calibration model. So they are neither inliers nor outliers, and we can therefore trust the values and report the predicted values for these new samples. So what I've shown you then is running the prediction on new samples within the Unscrambler, where I chose to have it also compute inliers and outliers. And from this we can get the standard error of prediction if we include our Y reference value, but more importantly, look to see if our samples are similar to our calibration samples in terms of the deviation, as well as making sure that they are not outlying samples. Today I've shown you the Unscrambler X, a general purpose multivariate analysis and design of experiment software. We do hold live training courses, and some of our next courses will be in New Jersey in December, as well as in Cambridge, England in November. You can check our website for times and places for courses around the globe. We do also have a support portal which you can access from our website. You can access it down at the bottom of the website, Service and Support, or indeed under Contact Us. And here you can enter your support questions and issues, and they'll be addressed within 24 hours. Within our support portal, for those of you who are our support customers, you can also get updated product news and download new updates to our software and upgrades, as well as access featured videos and other interesting information that can be helpful to you in learning more about multivariate analysis and the Unscrambler. We do also, within our website, have archived copies of previous webinars like the one today that you can access under the Webinars Training Webinars tab. And I encourage you as well to sign up for our newsletter, which is written on a monthly basis and provides you hints and tips on using our software and interesting applications that others have used our software for. So with that, I thank you for your attention, and I'd be happy to answer questions from anyone who may have some. So does anyone have any questions? Okay, one question is on importing data. So what we can do in importing data is we can show you actually, I will show you that when you import data, when you have data that includes text and numerics, the software does recognize that for you. So I will import some data in Excel that does include this. So I'll choose a data set here where I have text and numerics, and choosing File, Import Data Excel. And you see that here I have a column of text, and I also have numeric data. These are some economic data, and if I had data in different sheets, I could choose that as well. So when I import the data into the Unscrambler, it adds a new data matrix that I've imported, and I can take this text field, and the text will be shown in blue, and I can leave it as text, but I could also make that into a category variable, because indeed in this data what I have are economic data of different countries in Europe, and this column called region is actually a descriptor, a category about which region of Europe these countries are located in. So it is actually a category variable. So I can select this column, right-click it, and change the data type to category, and I can have it create that category based on the individual values that are in this column of region. So clicking OK, it's now created that, or changed that to a category variable, and then my column is now shown in orange. So that is how we can import data that are a mix of text and numerics. Okay, there's a question about doing a principal component analysis on a larger data set. The PCA analysis demonstration I showed you was indeed on a small data set of just some JAM data where I had just 18 variables. I can, of course, do a PCA analysis on very large data sets where I would have many, many variables and different types of samples. So let me show you an example of doing this. I'll import, again, a different data set to illustrate this example, and I'll import data that I have in another Unscrambler project. So I come to Import Data, Unscrambler X, and what I'd like to do is import data from this project I have called Classification. And what I'd like to do is import the data here wherein I have, this is showing me all the different matrices, models, as well as data that I have in the project that I'm importing from. And I'd like to, from here, import the data where I have some data on Raman solvents. So I'm importing that data to this project, and it's maintained the organization of that data as I had it in my original project. So this data matrix that I've imported, you may be able to see in my lower right quadrant, this data matrix is of a dimension 120 by 2205. So that means I have 120 rows of data, 120 samples, and I have 2,205 columns. And those columns include variables describing those data, indicator variables, ethanol, methanol, toluene, a category variable of what the type of solvent it is, and then I have columns from number 5 to 2,205, which are actually Raman spectra of these data. So I can make a quick plot of these data, choosing to plot all my samples and then my columns of spectral data. And here I see the line plot of my data. So each one of these samples, 120 samples, is comprised of over 2,000 variables. So I can run a PCA analysis on these data by going under Tasks, Analyze, Principal Component Analysis, and again, because I have numerous data sets, I need to make sure I choose the correct data set. So my Raman solvents. I would like to use all my rows, and for my columns here, these 2,201 columns, spectral data. Okay. Again, the software defaults to a maximum of 7 components, and I will keep that as such. The instrumental data are all measured together, so I don't apply weights, but indeed I do always do a validation. Here, I will not do a full cross-validation. I'll actually do a random cross-validation with 10 segments, which is what we recommend if you don't have any special groupings or such in your data. So this keeps 90% of my samples in the calibration and 10% out as cross-validation as it iterates through building up my model. So clicking OK, it now, you can see in the lower left corner that it's computing my model, and it's actually performing the cross-validation now across the 10 segments that I've defined. So it takes a little bit longer because of the cross-validation rounds, but it's only a matter of seconds or minutes. And it's important that we do our cross-validation. So now my PCA overview is available to me. And here I have my scores plot. Again, calibration and cross-validation depicted here. So I toggle off my validation. And I see that within this data, I have 3 distinct groups, which actually is indeed what this data set is comprised of. The data set is comprised of samples of 3 different groups of solvents. So I can again right-click and add sample grouping to this data set, to this plot, by choosing my categories, here, my row sets, and applying that, and I can see very clearly those 3 groups color-coded here and adding the legend defining what they are. My loadings, as its spectral data, I would like to see as a line, much like my data. So this is showing me that indeed 54% of the variance in my data, which is mostly separating this group from this, is related to these variables in my data. So there are some variables that indeed are not contributing much in explaining the variance in this data. Okay. Well, as there are no further questions, I'd like to thank you all for joining in our webinar today. I'd like to encourage you to download a